This is the most peculiar circuit I have ever designed. It runs very slowly in order to not bog down the simulator, so I had to turn down the simulation's processing speed. But the time step is 1 millisecond. Everything about this is precisely tuned to resonate in this condition of not only over unity, but self-oscillation. So the time step is significant. The values of the components, the equivalent series resistance of this capacitor, if you look in the lower right, ESR equals 1 E ohm. That's, I think, ecta or exa. I think it's exa. I'm not sure. Anyway, it's 1 followed by 18 zeros of resistance. And now let's look in the lower right again. What do you see? VD is the voltage difference between the two plates. 0 voltage difference between the two plates. Doesn't mean it's not there. It just means it's continually balanced. It never charges nor discharges. It's incapable of changing. It's incapable of charging or discharging. Yeah, changing. Yet, 232.83 gigaamps is registering. So it's like passing through it or around it. Not through it, obviously. It's interacting on either side as if it were invisible. It's as if it were not there. And what that means is I've eliminated, by eliminating charge and discharge, I've eliminated saturation. See, the saturation of components is the bane of that component. In particular, I'm thinking of caps and coils, capacitors and coils, capacitance and inductance. When we have to deal with saturation, take coils for instance. The saturation of a coil has to do with back EMF, because once it becomes saturated, it undergoes inductive reactance, which is the kick, the reverse or inverted kick, that it kicks out a good deal of energy to neutralize the energy you're pumping in. 10-30% is kicked back out at you in reverse direction to neutralize the current, and in reverse direction to the polarity of the voltage, I believe, if I'm not mistaken. And that consumes a lot of power to run a coil, such as a motor. Well, if we look at the capacitor, there's no saturation occurring because there's no voltage. And then when we look at the inductor, we see something peculiar happening. The voltage remains the same. It never varies. It's just the current ever so slightly oscillates up and down. Okay, that's the inductor. Now we look at this capacitor and something even more interesting happens. The amperage goes sky high to really low, and the voltage slightly changes. And to me, well, let's go back to the inductor. Well, it shows the other components are functioning, but not this one. So it shows that when you increase equivalent series resistance in a capacitor, that's if you take it high enough, that'll prevent saturation because it'll no longer charge or discharge. But yet, the 10 farads is still there. It still gives its influence of being there, yet it's transparent. It's a transparent influence. It's, I don't know how to explain it because this is so uncanny. It's like something out of the ordinary. Well, look, you can see the current is oscillating because it's there. You combine a coil with a capacitor in a loop, and you get oscillations. So it does its function of oscillating current, yet it does not participate directly. It says, hey, look, coil, I'm here. Oh, okay, now we can oscillate. So it fools the inductor, the coil, into thinking that it's going to play a role, yet it never participates in the role that it plays. it fools the coil into thinking that it's participating when it's not participating at all. It just acts like it's not there. It acts like it's invisible. Yet the coil doesn't know that. The coil thinks it is visible, and thus it goes into oscillations with it. This is what's so uncanny. And so what you end up getting is a very strange, I don't know how else to explain it. I'm sure there's more to it. That sounds too simple-minded to me. But the fact is you don't have to pay for the use of that component. You get all the benefit with none of the cost. And isn't that free energy when you can get all benefit and no cost out of a component? Then the component can give you what it was designed to give you without it costing your input to any degree whatsoever. Zero cost. That's a boost to the circuit. That's why this thing is running at 20 kiloamps plus minus, and I don't know what the RMS is, but if you take the average of 4 positive millivolts and 8, roughly speaking, negative millivolts, that's 4 and 8 is 12, is 6. So it's I don't know what the RMS is, but the average would be 6 millivolts if this were positioned. It would be 6 millivolts peak to peak if this were centered on the midline. And I think what I've seen happen over the course of running this simulation from its initial beginning is that everything was more in the negative end than it is now, while the positive end changed for the voltage, but not for the current. So let's go back. I did a screenshot. Not this one. This one. This is the one when it first I started it. So it had over 30 millivolts positive and roughly slightly more than 31 negative millivolts. So the voltage now has become more imbalanced. And the positive has reduced, while the negative has not reduced to the same degree. So now I have an imbalance more in the negative range. And then the amperage, it was always 1985 positive kiloamps, and now it's that still. But it used to be negative 39.76 kiloamps, and now it's negative 19.68. So it's coming more into balance in the amperage area, but the voltage has gone more out of balance, but it's reduced itself. So it looks like the voltage is reducing overall more than anything else, and that of course brought down the wattage. So now the wattage is balanced because all of the components are more balanced than they used to be, the component factors of, current and voltage. And so instead of 77 positive watts and negative approximately 77 negative watts, instead what it started out was 620 positive watts and 932 negative watts, which is a lot more watts, but also a greater division. It's 50% more negative than positive. So it's balancing itself. It's getting it more around the midline. You can even see, well, not really, because this is just starting out. Anyway, so it's a really bizarre circuit. It's strange in the weirdest way possible. And this is the shortcut, is.gd/oscillating earth battery. And I just got curious. I thought I'd run it for a while. It's been running in my time, real time, for a few hours. But in simulator time, it's roughly almost coming up on a minute now. So it's a very bizarre circuit. And everything about it would not be bizarre if it were not for this equivalent series resistance on this capacitor, which is quite high. Everything else, okay, yeah, 1 peta ohms of resistance, that's a little bit on the high side. But I found from prior versions of this, prior incarnations of this circuit, I needed to raise that under certain circumstances, particularly when I started adding in all these 100 microohm solder joint resistances. It changed everything. It made it more difficult to get over unity, and so I had to raise this equivalent series resistance to compensate for all these other resistances. So what I discovered when I was making changes to Paul Falstad's simulator, my mirror of his simulator, I went into the Java code, and that's when I got to learn a little bit of the mathematics behind electrodynamic theory. So I didn't get a formal training in this subject, but I did learn in the course of time, just by dealing with the open source software of Paul Falstad, some of the mathematical relationships. And one of the most interesting one is when I tried to add equivalent series resistance to both caps and coils, because he didn't have any. You know, LT-Spice and Microcap do have it there. By default, you can modify it, but Paul Falstad doesn't put it in there, and so you can't change what he didn't put in. And so all the coils act like they're superconducting, let alone the wires, you know, and the caps didn't have any either. Well, in a coil, when you put in equivalent series resistance, you increase its resistance. Now, it's already got the inductive resistance. That by design, that's the definition of a coil. But once you start putting in equivalent series resistance, now you're putting in the resistance of the wire itself, the length of the wire. You know, when you make a coil of a larger inductance value, basically a larger coil, you know, like a Joseph Newman energy machine, when you make a coil with a very long wire, you start getting a resistance to a very remarkable degree added to your coil, in addition to the inductive resistance. So it was the plane resistance that was missing. So I put it in by using wire gauge charts, and we can see here that I use as a default figure 25 og. You can change that, and that'll change the resistance of your length of wire. So I didn't use anything, you know, like 70 gauge in this particular example. Just 25. I just picked a random number off the top of my head that I thought would be a pretty good idea for a, you know, ballpark figure of what's an average wire size of a magnetic coil wire, you know, enameled magnetic wire. And then based on that choice and the level of inductance will determine the resistance. And so the resistance of this coil is roughly 10 microohms, a little less, 9.88 microohms, because of the wire gauge and because of the inductance. And so this is a realistic coil. It makes it harder to get over unity unless you know what you're doing. If you know what you're doing, it can actually make it easier depending on the type of circuit. You know, an unrealistic circuit, it'll make it harder, while a circuit that is not trying to circumvent reality by creating over unity, it could become easier. You know, it depends upon the makeup of the system. Now, putting equivalent series resistance into caps is right away a phenomenal event, because when you look at the math, when you put equivalent series resistance into a coil, it's a positive, it's an additional contribution of positive resistance. But when you put equivalent series resistance into a capacitor, it's a negative resistance. It generates current, while a coil eats it up. The length of the wire in a coil eats up current, but the equivalent series resistance of a capacitor accelerates current. Now, normally a ceramic capacitor has a default value somewhere in the vicinity of 10 milliohms of resistance, and that's my default is 10 milliohms. Actually, down here, 10 milliohms, see? But I can change that to whatever value I want to, large or small, and I chose to go 1E, which is 1 followed by 18 zeros. And that means that this now is supplying current. And that might be why there's no voltage registering, because it wiped it out. It's generating so much current, 230 gigaamps of current, that on either side, not passing through, because the dielectric won't allow it to pass through, but coming off of the plates in alternating fashion, is over 200 gigaamps of current, because now this has become a generator. Now it has to be tickled from the outside. It's not a normal generator, you know. But even a normal generator, you know, take a regular, like a, what do you call it? You know, a motor style generator, one that turns. You know, a regular generator. You got to have a prime mover, something that turns it, you know, like a waterfall. Turns a turbine, and then the turbine rotates a shaft, and then the shaft rotates the shaft of the generator. So you got to have something exterior. So it's no different here. except it amounts to being, the difference is it amounts to being very little. A tickle is all that's needed. And that's the secret to over unity, is you never try to use brute force because you'll just squash it. You'll kill it. You have to tickle a circuit that's properly constructed to create over unity, and then it'll give you what you ask for, but you have to tickle it very gently. It's like a little baby. Or I prefer to think of it not as a baby, but as a ember. You know, when you start a campfire using just a glowing ember from last night's campfire, you know, you want to start, you know, wake up in the morning and you want to start breakfast, and you don't want to go to the trouble to light a match because you've got a limited supply of matches on this trip. So you try to look inside your campfire from last night to see if there are any glowing embers, and you start a fire from just one of those embers. It's a very delicate procedure. You got to start with tinder, dry grass, and then you work your way gradually up to little twigs and then larger branches. Finally, you get it to the point you can put in a log. But if you put a log in that campfire from last night, nothing's going to happen. You got to start building it up gradually. And that's the way you have to look at free energy when you construct a circuit. It has to be so designed to take a tiny amount, an ember of energy, so small you cannot even measure it with measuring tools, although the simulator will show it to you, you know, but it doesn't mean you could actually measure it in the real world. It would be so small. You have to start with something so small that, you know, it's ridiculous how small, and then you very gingerly tickle it just the right way without ever squashing it. You know, you don't want to be a fat lady sitting on its face, or a fat guy. You don't want to be a fat person. You don't want to be a battleship running down a little tugboat. Or as Maharishi Mahesh Yogi would like to say, when somebody would ask him, why don't you help that person over there? He would say, not take cannon to shoot ant. That was his way of saying, I'm not helping him. I not take cannon to shoot ant. You know, he was a pretty powerful guy. And it's a pretty appropriate expression, even though it sounds like bragging, but it's realistic, you know. Hey, I don't want to blow the guy out of the water. He might kill him, you know, might send him to the psychiatric ward, you know, who knows? May go on a rampage and start killing people. Who knows? Could have adverse effects. So you have to be very careful, see. So when I started this circuit, I used a battery of 700 millivolts because I determined that was the limit that I could give this. If I went any higher, I wouldn't be getting this situation at all. So everything is very carefully designed to coordinate with each other to create the current condition, the present condition that you see in front of your face. If I had raised it to 800 millivolts, it would never have reached this state. It would have been lingering there in a state of mostly dead. You know, the circuit would be there, alive, but so nominal that it would be, again, you probably wouldn't even be able to measure it, or if you did, it would be like, oh, that's nothing. I get that just by wetting my finger and sticking it out in the air. You know, I get that as much voltage standing barefoot on the grass. Literally, not figuratively. So it's all about care and consideration about how you craft these things, because it's like putting together a Swiss watch. I mean, literally, all the parts have to work together to create the whole. This is not a flashlight circuit. This is not about brute force. This is not the way to solve the transatlantic telegraph cable problem that the Royal Society of London and also another fellow here in the States thought, oh, just give it more brute force, more voltage, and then we'll be able to send it across without relay stations boosting the signal across the ocean, because we can't put them there. In fact, we didn't invent relay stations until 1956, transatlantic or oceanic relay stations. But how did Oliver Heaviside solve it? He solved it because he went into the mathematics and he created what's now known as the telegrapher's equation. You can go look it up. And with that equation, he realized, okay, what they got to do is not try to give it more voltage, but wrap an iron wire or an iron ribbon around the insulated copper core, and he invented coax. But coax, in which the shielding, the outer shell, is made of magnetizable material, and the inner carries the voltage, while the outer carries the current. it becomes magnetized. And that boosted the signal, and the two signals came out the other side and were able to mesh and give us a telegraph signal, because without that meshing of the two portions of a live circuit, the magnetic field and the electric field, you get nothing out the other end. It's like static or noise or something. It's not even noise. Um, it's not electricity, because the magnetism disappeared. The magnetic field dissipated so rapidly across the ocean. The copper wire could not carry it far enough without assistance. Well, while the iron wire could. Because if you do an experiment, I did this, you take a neodymium magnet and wrap an iron wire around it. Excuse me, I'm losing my voice. A 10-foot long piece of iron wire, insulated iron wire, I suppose, you know. You go to the floral station, sewing, a place where you buy sewing stuff, or any place, flowers, you get floral wire, it's called, or the hardware store. It's insulated floral wire. It's iron with a plastic or vinyl coating to it. And you stretch out a 10-foot length, and you take your little compass at one end, have a helper help you, hold it up, and the other end you wrap around a neodymium magnet. You will find the compass react to the presence of magnetism at the opposite end of the wire to that neodymium magnet. Literally, the magnetism gets carried all along the length of that wire. And it's amazing what an iron wire can do. And back in the day, 100 years ago, they did that. They would run, Nathan Stubblefield would run two wires. One was copper and one was iron. So he knew what Oliver Heaviside did, but we've forgotten that. In our high tech, we've forgotten about the simple physics of electrodynamics, and instead the physicists get all the glamour and the glory, while we get nothing. There's no major research in electrodynamics anymore, unless it's for the military, and we don't hear about it. But not in a scholastic sense, because we think we've figured it all out, when in reality we're ignoring portions of the knowledge because it's bad for the corporate model. The corporate model of the economy is we need to spend more money, not spend less money. And that keeps the value of the dollar up. That keeps the corporations happy, including, what am I trying to think of? Banks and banking and the economy in general. Meanwhile, the quality of life for the whole population of the planet goes downhill, because it's all between the haves and the have-nots, and the ones in the middle get squeezed, and the ones at the bottom get squeezed. Well, they've always been squeezed. And the ones at the top keep shrinking in population while they get richer and richer because of inflation. So money is not making an improvement of quality of life for everybody on this planet. It's actually going downhill because of that. Technology does spread, and technology does cheapify. It economizes things by making things cheaper and more readily available, but service-oriented things still remain when they don't have to be, like plugging into the utility grid. They don't have to be. And this is what I endeavor to show in an idealistic virtual reality of the simulator, that overunity is inherent in electrodynamic theory. The robotic simulator doesn't know the difference between the ether or public policy or corporate policy. It doesn't know anything about that. It doesn't know anything about economics. Why do we need a utility grid to have somebody to pay money? You know, it is certainly not for energy. And so the simulator doesn't lie. It does not lie. You do have to interpret it because it's an oversimplification of reality, but it does not lie except in rare circumstances. And Paul Falstad's simulator, unfortunately, in today's model, it's not as good as it used to be. So I'm sorry, I have to take a call. So that ends this recording. If I can turn this off properly.